Hey guys, it's Steve again. Today we're going to start lesson 3, which is where we're locating offsets of memory with the mem commands and even with use with the offset command if we need it. Um, as I'm doing these tutorials, I'm learning along with you guys. I'm learning what works best for me and what works best for the tutorials. So my format's changing a little bit over time. And I think what I have here today is going to work a little better for me than what I've had in the past, where I just go along as I go. To start with, if you look at the screen, you can see I've kind of built me a little rough study guide of what I want to cover. And with this lesson, what we're going to cover is, well, like I said, the location of our offsets in memory. So when we use the memput and the memget commands, we can put the memory where we want it to go. Now, to start with up here, I've already dimmed some variables. It's simple enough. A B for a byte, I for integer, L for long, I64 for an integer 64, and M for a mem block. Now, if I want to point my mem block at these variables, it's as simple as just doing so. M equals mem of B. So we're now pointing our memory block at where B is located in memory. And if we want to put a value into B, that's all it is to it. I'm putting into my mem block M at the starting offset, M dot offset. Remember, M dot offset is one of those things that the mem command here generates for us. There's other things that are automatically generated for us as well, such as M dot size, which tells us the size of the mem block. And we'll go over some of the other things soon as well. But this is all it takes to put a value directly into memory. I'm not using the variable, I'm using memput, and I'm directly putting it into memory there. Now, I can do the same thing for my integer, and it's the exact same command after I got it. So, I'm not freeing my mem block here because I'm still using it. I'm just changing it from pointing to B to where it's now pointing to I. I don't need to do a mem free in between these two statements. I'm not causing a memory leak. I'm just taking my memory block M and I'm moving it from pointing to one place to pointing to another place. So it's no longer pointing to B, the variable B. It's now pointing to the variable I. So I'm now putting it where it points now. It's pointing to I. So I'm putting in memblock M at the beginning of it an integer. So in my integer I, I'm putting an integer value. The same way if I want to go through with a long, if I can type, and my integer 64 all works the same way. Notice when I'm putting my constant values in here, I'm defining them as what I want to put them in there. I've explained this with the last lesson, and it is an important thing. This fills up the whole block with the value as an integer 64. If I just put it as a byte, I'm only changing the first byte of it, which may leave values over from before. It doesn't fill the rest of the 7 bytes. An integer 64 is 8 bytes. So if I only put 1 byte, I'm not changing the second through the 8th byte. I'm leaving those 7 bytes, whatever they were. And I doubt that's what I'm wanting to do. So what I'm wanting is to put this number as an integer 64 and fill that whole little memory space. And to test it, we can just print these. And run our program. And if we compare our values, 127, 127, 98, 76, 98, 76. What we typed in is what our values are. So that's all it is to go and point a mem block directly at a variable. All you do is define your mem block, take your variable, and point it at it. You really can't get much simpler than that. So if we're going to do the same thing with arrays, I'm going to start with base 0 in my arrays. And that's what I've got here. I've already wrote it up with my little study guide as I go along. So I have 4 arrays. B10, it's an array that holds 11 elements. It starts at 0 and it goes to 10. And if we count those, and we start over here, you can see 0 is the first element. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. We have 11 elements in the array. So just because it says 10, it's not 10, it's 11, because we start with 0. Count the numbers for yourself if you need to. There's 11 numbers, 11 indexes or elements in our arrays. B is once again a byte, an array of 10 bytes. I10 is an array of 10 integers. L10 is an array of 10 longs, and I64 is an array of integer 64s. M, as I commented, is still our mem block. I don't need to redefine it. It's doing the same thing that we did before. We're just going to move the what M points to. And we'll start with pointing M at our byte array. And if you notice the syntax here and compare it to what we had before, here when we pointed to the variable b, it just was mem b. But if you look down here, it's mem b with brackets after b. These brackets says that this is an array. So this is saying don't point to the variable b, point to the array named b. So now we're pointing our mem block at the array B. Once we point it there, we do just like before, and we put a value in it. And there it is. Now this is putting it in M at M dot offset. Well, M dot offset is the beginning of our array. So the first element in our array, it's not element 1. These arrays start at base 0. So we're putting this in element number 0. We're putting it in the first element, the first index that the array contains. Now if we want to do the same for any of the others, it's the same index, the same syntax. Mem I with the 2 brackets says we're pointing mem now to the integer array, and we just want to put a value in it. And here we want to put an integer. And yes, I'm being lazy and doing a copy paste. Most people do that. And for our long and our integer 64, it's the same thing. We just simply make certain we put our values as a long or as an integer 64. And I'll change the values a little bit here so they're unique numbers. And to point to element 0 in these arrays, this is all it is. It's point your mem block at your array, put it at the beginning, which is M dot offset, and put the value you want. And to print them, we can now run it, print it, and here's our numbers: 12, 21, 34, 102, 215, 67, 34. So, to go to the first element, there's nothing to it. Just mem put to your memory block, to the starting offset, and then the value as the type of your array. So, there's nothing complex up to this point. Now if we want to point to a position which isn't in those first elements, let's start back with our byte array. You still point your M at your array. You point your mem block to your array, and now you go to the offset and you move over the index you want to go to. In this point, I want to go to the 3rd index, and you multiply that by the size of your variable. B is a byte. A byte is 1. It takes 1 byte. And then I put a value in it. And this should be element 3. Now, for our integer, the same thing. You just point it to it, memput, and I'll go to the 7th element here. But integers are 2 bytes each. So here it's times 2. And then I put my number into that position. And this goes into element number 7. So the size is important because you have to have enough memory to hold your variable. A byte only uses 1 byte of memory. So with an array, the first byte is 1 byte. With an integer, the first byte is 2 bytes. So for every index, you have to move over 2 spots. For a long, it works the same way. Only it's 4 bytes. A long is 4 bytes long, so it's the times 4. And this will go in element number, what I put it at, 2. And your integer 64 finally I'm getting ahead of myself on my typing. This says I'm starting at my offset, moving 9 spots over at 8 bytes each, which is what an integer 64 is. An integer 64 takes 8 bytes in memory. And then I'm putting my value. And then we print to make certain we get those values where we want them. Get my print statement. And when we run it, we now see a third set of values directly where we put them in memory, in the third byte, the third index, the third element of B, we put 23, and that's what we're seeing up here. In the 7th index of I, we're putting 546, and so on. We chose which element we wanted to put it in. We tracked the size manually, and then we put it, the value, in that position. We're directly putting values into memory, and we're bypassing the way that you'd have to do it with arrays normally, such as B sub 3 equals 23. There's nothing wrong with doing it this way, as I've got highlighted here. The only thing is, it's slow. QB64 has a lot of error checking built in, it checks to make certain b is a variable, that 3 is a proper index, that everything is going where it should. Then it looks up where in memory it needs to go, how much memory it needs. Finally, it looks into the memory. It grabs that value that you're wanting to put into it and it puts it in the right spot. It's a lot of steps behind the scenes which goes on for this little statement. If we need speed, if we're doing a program that's intensive and needs speed, it's much better for us to put our memory there ourselves and skip all of this behind the scene work. If I want to put a value in my array, just put it in my array. Don't run through the hoops of using B3 to put it there unless I just necessarily have to. If you're doing things like sorting arrays, it's much faster to get the arrays 1,000 times from memory directly than it is to go through that lookup table and look them up behind the scenes and get those values and put them and swap them and compare them. So this is the main purpose of MIM. It doesn't make it simpler to type it, and it doesn't make it simpler to code. There's a lot more coding going on up here than there is down here. But it's a lot faster if we execute them. But you might say to yourself, well, this is a good bit for me to keep up with. And you're right, it is. So you'd have to think, is there anything that we could do to make it a little simpler for my poor befuddled brain? And here we're going to talk about a nice little trick. Just like m.offset equals the start of our memory, and m.size equals the size of our mem block in memory. We have another keyword here, element size. M.element size is the size of an individual element in that mem block. So how can we make use of m.element size? Let's start back up here by pointing m to our byte array, if we can. There. And let's put some values there. Last time I put it in value 3, offset 3. This time I'll put it in offset 5. But I don't want to have to worry about the size. So there we go. We let QB64 tell us what the element size is. And this should now be in element number 5, or index 5 of our array. And it's putting the value 12. Well, we can copy paste to save a little copying and typing, since I can't type worth a hoot. Point to our integer array, and instead of having to manually track these sizes, on all of these, we can instead let QB64 track our size for us automatically. When we're dealing with a byte array, it knows the element size is 1. If we have an integer array, it knows the element size is 2. Longs are 4. This is what m.element size tells us. It's very similar to just using len, L-E-N, to tell the length of a variable. And I'll point these to a few different places. There. And change the values slightly. Change that. There. And now we have those values again. And we'll print them once more. Element 5. Element 3. Element 8. And element 1. So now, without us having to manually track it and remember what the element size is, we've got it going where it should. We still have to track what we're putting into it. We're putting a byte, we're putting an integer, a long, an integer 64. So you can't completely forget about everything at this point. But that's all you do here. And when we run it, there's our changed values in the element positions where we put them, in the indexes where we put them. I put it in the 5th index here, the 3rd one here, the 8th one here, the 1st one here. And m.element size automatically tracked those values for me, which is really useful when we're working with a type of variable. If we do our custom type, and I'll do one for us for an example, type. Okay. And dim a variable to it. Dim. So now I have a variable called example type. And I want to make an array. And at this point, EX is my array. My array of 10 as an example type. And here I can add it up. An integer's 2 bytes, an integer's 2 bytes, 2, and then my string I've defined as 20. It gives me a total of 24 bytes. So this isn't a complex user type, but some user types get quite complex. And over time, as you work with your code, you'll realize later, well, my hero, I don't just need the XY position and his name. I might need to know his health. And then you go back and you add another element in here, H for health. And suddenly, all your code where you hard-coded a value, you have to go in and change and increase the size by 2. Whereas if you used element type, you don't have that worry. Or element size, I'm saying element type, I'm sorry, I'm talking about type, so I'm getting my keywords confused. Now, here, the very first thing I'm putting into this would start at the beginning of the offset for my example type. So when I'm putting 1234 in there, I'm going to put an integer into the beginning of this. Then I'm going to put 2 bytes over. So I still need to know a good bit about my type and its positions. But it makes it easier for the math. I don't have quite as many numbers to remember. And here, this would be X in the 4th index. This would be Y in the 4th index. And this would be my string in element number 4. Now, if you look, this is at m dot offset plus 4 times the element size. So I've moved over 4 whole blocks of my example type. I would actually be at position 4 times 24, 96. This is byte 96 in my array that I'm putting in my mem block that I'm putting 1234 into. This would be byte number 98 and this would be byte number 100. So I'm moving over 26 because I didn't update my total. And that's what I was saying about the biggest advantage to using m.element size rather than hard coding those values. Because if your size changes, such as in my type when I came along and added the health parameter, and I don't have anything in my health parameter here. So let's put something there. And now I'm putting 12 in here for my hero's health. My hero is going to start on my map at position 1234, 4321. That's his XY coordinates. My hero's name is Hello World, and he has 12 points of health. And we can print this. Example 4.x, example 4.y, example 4.s. And when we print it, there's our values just as we wrote them in index 4, because here we moved over 4 positions. 4 times m dot element size. Starting with byte 0, we put an integer. That's x. That's our integer here. Then we move 2 bytes over. This is the size of x. So we moved over 2 bytes and we put y. We moved over 2 bytes past that, 4 bytes from the start of that position. Now we put the string hello world, and then 24 bytes from the start of that array element we put our health. So it's still a little bit of tracking things manually, but the advantage here is you only need to know these numbers once. Scribble them down on a piece of paper, scroll up and look at them, give yourself a running total, whatever you need, like here in my little notes. And then when you go to get inputted, you can just look back for quick reference and say, oh, well, I don't want the total size, I want the offset. So there's my quick notes. This starts at 0, this starts at 2, this starts at 4, this starts at 24. So 0 plus 2 gives me the 2, 2 plus 2 gives me the 4, 4 plus 20 gives me the 24, 24 plus 2 gives me 26, 26 gives me m dot element size. The total size of our type is m dot element size, 26 bytes here. And this fills all 26 bytes with information, which we then print out down here. So at this point, we're really not dealing with anything overly complex still. You start with bit base 0, it's m dot offset, plus the index you want, times the element size. And if it's a type, it's a little bit more to keep track of, because you need to know what you're putting into each position in that type. You could put the whole thing into your offset at once, which would be and to do this, I'm going to dim me a temp variable, a temp string, and dim temp. I'm going to make it a string of 26 bytes. Now, here's an issue you run into. You have to put a number or a constant after a string like this. So here you would have to hard code that value 26. So it works. Or you can make certain that you keep 26 bytes for a string to put into it. And At this point, I could put either of these, temp or temp1, into my array at this point, and of course it's all going to be zeros. I don't have anything but spaces, which are all blank, so there's not going to be any point to printing it to this. Well, in fact, it's not going to be zeros, because a space is a ASCII ASCII character number 32. So what I'm actually putting in there would be CHR string 32 plus I'd be putting two CHR strings 32 in there, which in hex gives us a number. These are ASCII values. If we convert this over into an integer by looking at it in memory, we see that these spaces are given a value 8224. This is CHR string 32 and CHR string 32. We put it into our memory as strings, but then with our type we read them as integers. They're not CHR string zeros, which represent 0. They represent the ASCII value 20, or the hex value 20. So what we're actually printing here is not F0, 20. 16 and 16 is 32. Yeah. And H2020. This is CHR string 32. This is CHR string 32 represented as a hex number. And as you can see, that's what we're putting in there. So we're not really putting zeros, as I said. We're putting spaces, which they do have a value. So once we have our string as we want it, we assign it a value. And now I'm using the MKI command. This is to make a number into an integer string. So it's taking the 1, 2, 3, 4 and the 3, 4, 5, 6, and this is turning our numbers into strings, 2-byte strings, which are the integer equivalent of it. And now I'm going to let that print all at once. And when we see what comes up on the screen, we're getting 1, 2, 3, 4. See, I made this into a string, but I'm reading it as an integer type, because when I wrote my string, I wrote the string equivalent of 1234. Uh, as we write data, you'll find with mem commands, they're quite fluid like this. That's why you find what works best for you. Sometimes, to compare two strings, if they're 4 bytes each, if we want to compare if these strings are the same, we could read them as longs instead of strings. QB64 has some inherently slow string commands. So, working a little logic behind the scenes, we can read it as a long, compare it to another long, and do it much quicker than we can by reading a string and comparing it to a string. The number comparison routines are much quicker than string comparison routines in QB64. And here, that's what we're doing. We're turning this number into a 2-byte string, this number into a 2-byte string, and then we're putting a hello world. And since I didn't bother to count how many spaces that was, I didn't put any health on this one, which is why I didn't bother to print it. If I wanted to count out 20 spaces, I could then use MKI and print another value as an integer. So, one put statement here puts the value where I want it. Now, if I would have started out and I better check my syntax. Nope, I got it backwards again. Using the string command, 26 characters of CHR string 0. Now here, it's what I was saying. I print it. There, our values are actually 0. They're CHR string 00, which is the value for 0. CHR string 32 and CHR string 32 gives us a value of 8224, which is what we've seen with that other program, and I'm getting quite a few of them up here now, so let's stop a few. So we can put things in our memory where we want and what we want, which is why it's important to keep track of these offsets. QB64 doesn't track them for us any more than it does when we get input to a file. If you remember my first tutorial, I compared these commands to get and put. If we were writing to a file, this would work the same way. We can put these values directly to a file, just like we're putting them in memory. And we can read them back in this same odd manner directly from a file, just like we're reading them here. So, my note says nothing's complex to this point, but it is getting a little bit complex because I went ahead and went into our types a bit. But it's still not bad, because basically what it breaks down to, and what I'm trying to illustrate here, is the idea that when you start with a base 0 element, you just put into that position plus the element size. Either you manually track the size as I did in these first numbers, or you use the element size and you put your values into the proper index, m.offset plus 5 times m dot element size up here, which is what I did to put it in B5. And even with types, it's a little bit of manual tracking that you have to do here, but the base ideal is the same. You start at your index times your element size. So the trick at this point, when you're dealing with this, you want to remember, and here I'll write a little note so to go on here. The offset for base 0 arrays, and this is what most arrays are. Most people will dim an array 10 or dim it 100. So the offset for most base 0's arrays index is always going to simply be your index times the element size moved over from the starting offset. So this is where you're going to put most of your information, or get, if you're using memget and you want to get these values directly. So you're just getting and putting to these positions when dealing with a base 0 array. It's not really that complex. The types make it a little more complex because we have to track each of these subtypes, where they're positioned, so we put our values properly. But for the main type itself, they're positioned in the same spot. So that's where we're going on, and we've got everything settled to this point. And now for the third part of this tutorial, we're getting to oddly indexed arrays. I'm just going to redim my arrays, which is why I used redim before, so I don't have to come up with new names. As you can tell, I don't have the greatest naming sense. I like keeping things simple, particularly for a tutorial. So B is still our byte array, but this time our byte array only has 3 to 10 elements. Our integer array is still I, but it goes from -4 to 10 elements. Our long array from -8 to -5, and our integer 64 array from 10 to 100 elements. And of course, mem is still our mem block. So, to point to the first element of these arrays, well, the very first thing, since we redimmed these, my last mem block that I pointed to was pointed to EX. Okay, so I can't show you nothing at this point. If I would have left it, and here I'm going to cut this out of my code for a minute. Just remove it. So I'm not printing anything to those points. Now the last thing that my mem block is pointing to is my integer 64 array. And I put a value into the first element. Well, here I'm going to put a sleep command so I can pause my program at this point. And I'm going to change that value simply from positive to negative. And a print statement so we can see it print. And let's see what happens. I had an array, I redimmed it, It was pointing at integer 64, at my integer 64 array. Everything looks like it should. Oh no! My memory's been freed. Line 77. My memput doesn't work because I've got a critical error. 1308. My memory has been freed. That crashed my program. This is what I wanted to show you before, at the beginning anyway, to help highlight the fact that that's what happens when you screw up with MEM. You crash your program. You should debug this before you give your program to the public, or it's going to crash for them. But as a programmer, wow, I crashed it again. You won't believe how many times I've crashed things. I wouldn't even want to count. If I had a penny for every time, I'd have a big bucket load of pennies. So why did it crash? Well, the error message, it tells you your memory has been freed. Anytime we redim our variables, we free any mem block that's associated to them. Why do we do that? Because they move in memory. Up here, when I first dimmed, way up here where I first dimmed B10, it was pointing to a spot in memory that contained 11 bytes. Well, down here, I changed it. I no longer need 11 bytes. I've got 8 bytes. 7, 8 bytes, whatever it is, 8 bytes. I've got 8 bytes of memory here. So it freed that 11 byte memory block, and it reserved 8 bytes for B. So I'm no longer pointing to the same place. For the old integer 64, which is what I was pointing to up here with M equals mem I64, for the old integer 64 array, it had 11 elements. Well, now it's got 91. So it had to free those old 11 elements, and when it did, it automatically freed that mem block for us. So we have to point it once more towards a valid mem block. And to do that, it's just like we were doing it. But this is an important step. Make certain anytime you use a redim command, you repoint to your memory block. And if I run it here, once again, we generate an error. A different one this time though, because this is still a memory error, line 77, subscript out of range, continue no, because I want to put it in I64. I don't want to point to one specific element of an array called I, which is where I was pointing to. I want to point to integer 64, the array. A typo, which crashed the program. And now when we run it and hit space because of the sleep, another error. But this one says subscript out of range, continue, no. It's on line 79, and that's because when I copy pasted and changed things, my index now runs from 10 to 100. If you notice, here, I didn't get an error on line 78, but I got it on line 79. Why? Because when I changed this to look to the 11th element, I'm now getting the value that I've got here. It's putting it, where does I-64 start at in memory? It starts with element 10, because that's what we've got our array indexed at. And I'm getting a little ahead of myself here, but when we move one element over from 10 is 11. And that's why this gives us the value here that it does. Now I'm going to take this sleep out. I mainly wanted to show what happened when we redim without repointing to a value. So let's take all this out and now get back on our proper tutorial without going through all these purposeful errors and a few typos which weren't quite so purposeful, but still useful, I hope. So, as I was saying, to start with, we pointed at our array B. To put things in the first element, which is what the note here says, we can basically just copy what we had up here, well, up here where we was putting things in element number 0, and just repaste it down here. It's the same thing, the exact same thing we did before, except now we have to remember when we print, we're not printing B sub 0 now. 0 isn't our first element in the array B. We redimmed it. We're printing B sub 3. We're printing I negative 4, L negative 8, I-64 10. These are all the first elements in these arrays. This goes here, and our first element starts at m dot offset. And our second element is over 1 byte from this. So we have to keep track of our lower bound index. And that's really what's important here. Your true point of interest is the lower bound value of your array. And as we print these now, we'll see our numbers, since I did a copy paste, are an exact match. But these were pointing to the elements up here, 12, 50, 12, wherever I copied them from. I copied them from way up here. So yeah, these are the element zeros, and these are where we printed them down here where we copied them over, but they're not pointing to element 0 anymore. They're pointing to the first element in each array. So MEM doesn't track what the first element is for us. It just tracks where it starts in memory. So it's up to us to track the starting element. So when we want to go to a specific spot, I'll make me a comment here just so I can keep track of what each starting point is. We point, just like always, to the mem block we want to work with. I'm working with M is going to point towards mem block B here. Now, here I want to move to, before it was index times element size, and I wanted to put a value. And as you can see, here I'm putting a number that is bigger than a byte as a byte. So there's going to be some overflow, but I'm still only putting the first byte of that number in there. And I ain't certain what that'll be, but it doesn't generate an error for us. We're putting it as a byte, so we're getting 345 as we'd write it as a byte. And since that might confuse people, let's just print 45 as a byte into it. So this is what we was doing before, index times m dot element size. Well, what we want to actually do, we were doing something a little more complex than that. We were doing the index plus the lower bound value of our array, which in this case is B, and then multiplying it by the element size. And here, if I want to put it in the index from 3 to 10, I want to put it in the 10th index. And we print B sub 10. Oh no, a memory region out of range. Where did I get a memory region out of range? Okay, here's my error. I had my memory region going to index plus the lower bound. Well, that's not right. I need to move it minus the lower bound. When we're dealing with an offset that starts with 0, if our offset starts at 0, or our L bound starts at 0, then the formula is index minus 0. Times m dot element size, which is of course what I told you before. The thing of remembering was index times m dot element size. Index minus 0 is index times element size. But if our array doesn't start at 0, we need to move which index we want to go to by whatever the lower bound point is. And here, that's what I'm doing. M dot offset plus the index minus the lower bound times the element size. We're getting some semi-decently complex formulas going to find where we're going in memory. But not everybody is ever going to need this. Like I say, most people don't dim an array from 3 to 10 elements. But if you do ever dim an array from 3 to 10, this is how you're going to want to find your specific offsets. And when I do print B10, well, that's what I was saying up here. Index 10 minus the lower bound of B, which is 3, times the element size, plus putting my 45 as a byte. So, it's getting a little complex there. But as long as you remember basically this concept, index minus the lower bound of your array times your element size, the size of the array. You want to move it that far over for each index. You can put whatever you want into it. For I, it goes from minus 4 to 10, so index minus 3. And I do want to move my mem block to point to mem of I. And here we follow that same formula, put a value as an integer into it. And this is now going into the -3rd index of our integer array. And when I run it, once again I'm out of range. What in the hell's going on? Okay, we got a couple of problems here. First, I'm not pointing to my array again. A typo. I'm pointing to memory block I and not I the array. So I have to make certain to point to my array. And down here where I copy pasted, I don't want to point to the lower bound of B. I want to point to the lower bound value of my integer array. And now when I try to print things, I should indeed print 1245 into integer array -3. And yes, I finally got it correct. So, as I was saying, it's getting a little more complex as we go along. Typos are quite common, at least for me they are. Even when you know what you're doing, it's easy to get things off. But that is the advantage with the MEM system. There's a lot of safeguards built in here. So it's really hard to mess up your computer. All you can really do is what you've seen me do several times already. Crash your program when you run it. And it usually is pretty nice about tracking what the problem is and why you had it. Memory region has been freed. Memory is out of range. You're not looking in the right spot. Try again. So, I'm not perfect. You guys shouldn't expect to be perfect. I did this a whole lot. And as you see, sometimes I get myself confused with the mistakes. And a lot of times it's a simple mistake, but they're hard on the eyes and they're hard to catch. There's not a lot of difference visually between mem-I and mem-I bracket bracket. And the bracket bracket is very important because here I'm pointing to the memory of variable I, and here I'm pointing to the memory of the array I. So it's quite a different thing, and that's where my error was popping up. I wasn't even looking at an array, and I was trying to jump back several spots and look at a negative element outside the bounds of my memory, and QB64 said, no, you can't do that. So I had to correct it. And of course, down here, my lower bound for B, which is where I copy pasted, is 3 compared to I going to -4. So I was throwing my index off the chart anyway. So 2 mistakes is what I type. One just from copy pasting, the other one from leaving brackets out. So copy paste is nice, but it's not always your friend. And of course, typos are never any programmer's friend. If you ever write C, semicolons are the enemy of mankind. I hate semicolons in C. I forget them. The code looks right. My brain tells me it's right. And it never tells you you're missing a semicolon on line 3. It tells you return without whatever on line 9216. You have to debug the shit out of C to find where the semicolon's missing. At least from my experience, I do. But that's C and this is QB64, and we have our own problems. And for me, yeah, copy pasting is an error problem. Typing is a problem. And forgetting things like these little brackets which says I want an array instead of an integer, that's sometimes a problem. But to finish this up, let me get on with the next 2 little arrays are long. And try not to screw them up. Our indexes here go from -8 to -5, so my index would be -5, -5. See, already typos. And this is the lower bound of L because we're putting it into the array L. And that should put that value into index number 5. And if you notice, I'm not quite as confident myself that I don't have typos. So for each one of these, I've been printing them to the screen one at a time so I can test things to make certain I'm putting it where I want it to. And yes, there's the value in index number -5 of L -8 to -5. So that one's now where it should be. I got one without a typo. Aren't y'all proud of me? I'm proud of myself anyway. And here, for the last one, I should have a value in my integer 64 array in the 78th element spot. And yes, I have a value of -9. Where I put it, I got another one without a typo. So that's now got the values going where they should. And at this point, see, I knew things are getting a little more complex. They're getting a little more complicated and whatnot. And that's what my notes say here. Here's what I'm going to start with the next tutorial. We're going to be talking about multi-dimensional arrays. And if you think it's gotten odd up to this point and a little complex to find your point, the formulas get a little more complex as we keep going. And so I'm going to end the tutorial here. When dealing with odd indexed arrays, the formula you want is index minus the lower bound value of that array. And it's much better, if you can, to not use L-bound. That's a slow command. You're going out to a function, looking up a value, bringing it back. Mem, the whole point of it, when you're putting it in your programs, you want to speed it up. So if you have to look it up, look your lower bound point up before your do loops, before you start making the most use of mem. Don't do it like I did up here. If anything, have it where you calculate your index. Put it outside of a do loop. You want the fewest possible calculations inside a do loop as you can possibly have. If I want to change every pixel on the screen from red to blue, I want to do it as quickly and efficiently as possible. And the more complex my math formula gets inside a loop, the more I'm slowing it down. I'm adding processes. So if I can take things out and before a loop calculate the offset, do that. Save yourself that processing inside the loop. But I'll get on to optimizing memory blocks and how to speed up mem access and to make it prettier and all later. Right now, I'm just trying to show how to find your offsets for people. And like I say, when dealing with odd indexed arrays, the formula is index minus the lower bound value times the element size. And for base 0 arrays, it's actually the same thing. The only difference there is index minus 0, which would be our lower bound, is index. It's the index that we want to go to. The position, the element, whatever you want to call it. So, at that point, for base 0, we can take that lower bound statement out completely. And what we're using is just index times m dot element size. And remember, for both of these, we have to start at m dot offset plus that move over. So this is how we find specific positions for base 0 arrays down here, and this is how we find a specific position for oddly dimensioned arrays like I had up here. And I'll even copy this note one more time so it'll be easy to remember. So, like I said up here, these are offset to b sub 3, I sub negative 4, negative 4 to 10. It's very, very rarely that I've ever actually had to use an array with such odd offsets. But it has happened a few times. I've been programming for 30 years now. So it's nice to have a reference to go back to, or to at least learn it once for that odd time when it does come up. So when it comes up that your index is something odd, it's m dot offset plus the index minus the lower bound of the array times the element size. So it sounds complex. It simplifies down in most cases to something that's much easier to keep track of. But it's nice to know for if you ever do run into that really insane situation where you need such oddly defined elements. And as I was saying down here in these final comments, things are getting more complex at this point. Depending on time, I might end the tutorial with just this amount of information covered. And really, I think that's a good place for me actually to stop at this point, because things do get more complex as we go along. And next, I'm going to be dealing with multi-dimensional arrays and how they're positioned in memories. And a multi-dimensional array is like MB down here, 10, 10, 11 elements of one and 11 elements of another. This is also the same way we store a screen full of information. A screen image is right here. This screen image is 640 by 480. If I was storing it as an array, it would be wrote as an array just like this. Well, it would actually be just like this. And it would be long values, or truly unsigned long values. This would be a true representation of how a screen image is stored, because from 0 to 379 is 340 elements, and from 0 to 479 is 480 elements. So that's a 640 by 480 screen. Since it's 32 bits, that's a long, but it's an unsigned long. We store memory values for screen in unsigned bytes. Red, green, blue, alpha. And I did a little bit of explanation for those with tutorial 2. I'll continue getting on the screen images better with future tutorials. But that's where we'll be going with tutorial number 4. Multi-dimensional arrays and screen images, where a screen image is really nothing more than a specialized multi-dimensional array which we read and use to plot pixels on a screen. We call it a screen, but it's still the same as any other 2D array. And that's where we're going to tutorial 4, beyond the first dimension. So I hope everybody enjoyed this. I hope you could follow along with me. It's a little complicated. Feel free to ask me questions. I prefer you do it over at the QB64 forums rather than on the YouTube channel. But wherever you ask them, if you send me a private message, I don't care. If you ask me a question, I'll try to answer it to the best of my abilities. That's what I'm doing the tutorials for. But if you ask over at the forums, other people who might be curious about the same things you're curious about might find your question and find the answer there. So I'd prefer, if anyone has questions, to come over to the QB64 forums and post the questions there for me. I've got a topic for the tutorials, you can see it. And feel free to ask anything you want. And this is the end of tutorial 3. And we'll go on from this point. I'll pick up tutorial 4 in about a week's time. I want to give people time to see this. It gets, like I say, a little complex as we keep going. So I want to give people time to see it, time to take it in, and to play around with it a little bit themselves, so they can make use of this information. Because as we continue on, we're just getting deeper and deeper into the internals of how these commands work and where things are located and how to calculate more complex offsets as we go. So I hope you guys enjoyed this, and good luck.